Hey everybody. So I'm going to do a quick run through some of the methods we're going to have for manipulating what we call quadratics or quadratic. What I've written here is a quadratic expression. We'll see solving quadratic equations, and so we're going to learn some methods for working with these kinds of let's say mathematical objects, right? So in this expression, right, we're thinking of x as our variable, a, b, and c are real numbers, and the only condition on them is that a can't be zero. If a was zero, we don't really have a quadratic. The quadratic here, what we're referring to is polynomials. These are sums of powers of x, uh, positive integer powers of x, and quadratic means that the highest power is 2, right? So for each, the highest power, you'll learn later on, is what really matters in some sense for a polynomial. So we look at the highest power to categorize it. So anyone that has its highest power of 2 is a quadratic. Lines are really polynomials, with the highest power being 1, right? We often call that the degree. So the quadratics are degree 2 polynomials. Lines would be degree 1. So I'm going to go through a couple of methods in this video, and there'll be another video with a couple more. We'll start with what's typically thought of as the simplest quadratics, and move towards more complicated ones. And what we're typically going to be solving is equations that can be written in this form. Okay, they're not always going to come to us in this form, but if there's something that can be written in this form, these are the kinds of equations we're looking at and the methods we're going to look at. So I'm going to start with the simplest version, probably, something like x squared minus 19 is equal to 0. Okay. And so there's nothing too complicated we need to do here. We can simply add 19 to both sides, give ourselves a nice, we've got x squared equals 19. And then we're going to take the square root of both sides, being careful to remember, just going to move this to give myself a little more room, that we actually need to take both positive and the negative root here, right? For our square root symbol, we typically mean the positive square root, but we're not just taking the square root of something here. We're actually solving an equation. We want to know all the values that make this equation true. And so in this case, we get two results. X is either the positive square root of 19 or the negative square root of 19. Okay, and that's it. That's the value. There's no better way to write this number. We could write a decimal approximation, but that would only be an approximation, right? And to be clear, when we write plus or minus, what we really mean is that the values of x that make this true, or this equation is true, when x is equal to the square root of 19, or when x is equal to negative square root of 19. Okay, that's what we're saying with that statement. All right, let's push forward into something slightly more complicated. Let's take a look at an equation. Let's look at this equation. 2x minus 3 squared is equal to 4. Okay. Now, first of all, I just want to note that this is something that could be written in this form. All right, so let's do a little work off to the side here. This is 2x minus 3 times 2x minus 3. Expanding our terms, we get 4x squared. We'll get a minus 6x, another minus 6x, and a plus 9. So we've got 4x squared minus 12x plus 9. And if I put that back into this equation, I've got 4x squared minus 12x plus 9 is equal to 4, and I can subtract that 4 to this side. And there I have it in that form, right? And this is the case where a is equal to 4, b is equal to negative 12, and c is 5. However, I don't really want it in this form, right? I just wanted to point out that even though this doesn't look like that, it is that. It's just wrapped up a little differently. But this form that we have here is actually a pretty convenient one for solving this. I can go straight to the step of taking the square root of both sides. Again, plus or minus. And so I'm going to end up with, on this side, 2x minus 3 is equal to plus or minus the square root of 4, which happens to be 2. I don't know why I got so moved over. And now I just use my familiar rules of algebra. I've got 3 plus or minus 2. I'm going to multiply both sides by 1/2. All right, 1/2 times 2 is 1, so we're left with x. I distribute this 1/2. I've got 3 halves plus or minus 2 times 1/2, which is 1. And again, this is 2 answers. This means x can either be equal to 3 halves plus 1, or 5 halves, or x can be equal to 3 halves minus 1, which is 1/2. Right? And let's go ahead and check our work. Let's remind ourselves what we do when we solve an equation. I found 2 values of x that make the equation true. So let's see if that's accurate. If we go back to what we have, let's check for x equals 1/2. If I put in 1/2 for x, 2 times 1/2 minus 3 squared. That's 1 minus 3 squared, which is -2 squared, which is 4. And so that was our original equation, that you take this value, multiply it by 2, subtract 3 and square it, you'll get 4. Same thing for 5 halves. Let's check that. X is equal to 5 halves. We'll get 2 times 5 halves minus 3 squared. 2 times 5 halves is 5, so we've got 5 minus 3 squared, which is 2 squared, which is again 4. And so there are our 2 answers, our 2 results, our 2 solutions, the values of x that make the original equation true. So let's do one more of these. Let's do a very similar one with just one little complication thrown in. Let's take 2x minus 3 squared is equal to -2. We'll start the same way by taking the square root. Now, here we're either done if we're in a context where considering complex numbers is not appropriate, then we simply say there is no solution, right? There's no real solution to this, no real number. Again, don't let that word real make you feel like the other solution, the complex solutions are fake. It's just a name given to the kinds of numbers we have. Anyhow, but if we are in a context where working with, excuse me, complex numbers is valid, then what we get is 2x minus 3 is equal to, and let's do a little scratch work. -2, remember, is -1 times 2, which is the square root of -1 times the square root of -2, which is I root 2. So we get I, oops, but I forgot. This, again, needs to be plus or minus. All right, so what we're ending up with is plus or minus I times root 2. Okay? Remember, we treat I like any variable, other than the fact that when we square it, we get -1. And so I can use my familiar algebra, add 3. I get 2x is equal to 3 plus or minus I root 2. And I can multiply by 1/2 again on both sides. And I end up with x equals 3 halves plus or minus I times root 2 over 2. Or written out more explicitly, 3 halves plus I times root 2 over 2, or 3 halves minus I root 2 over 2. Let's check these solutions, right? It's always a good idea to check our solutions. So let's check x equals 3 halves plus, let's do minus. I'm just going to check one of them and I'll let you guys somehow write what my brain is thinking. Root 2 over 2. My brain, my hand and mouth apparently have their own intentions this morning. Okay, so we put this value in for x. So we take 2. So I'm just looking at my original expression. When x is equal to 3/2 minus I root 2 over 2, this becomes 2 times 3/2 minus I root 2 over 2. This whole thing is going to be squared. And, oh, I forgot my -3. Pardon me. I knew something was wrong. -3, this whole thing squared. So now manipulating inside, I'm going to expand by multiplying through by 2. So 2 times 3/2 gives me 3. 2 times I root 2 over 2 just gives me I root 2. And then we have a -3 squared. So now I've got 3 minus 3. Those disappear. I've got negative I root 2 squared. Let's do this carefully. I'm going to rewrite this inside as -1 times I times root 2. All right, that's what we really mean when we have negative I. Negative anything is -1 times that, or that's one way we can think of it. And so I think this will make it easier to track the negatives because we're going to have a lot going on. We're squaring negatives, but we're also going to have an I squared that we know comes out negative. And I think it would be easy to make some errors here if we didn't separate it like this. Now I can apply this exponent to each thing in here. -1 squared becomes 1. I squared becomes -1. Root 2 squared becomes 2. And so we end up with -2, which is what we expected, right? That was our original equation, that this thing squared, this 2x minus 3 squared, we're looking for values that made it work out to be -2, which is what we found. I'll let you check the other one. It's a good exercise in working with complex numbers, but you should come up with something pretty similar. Okay. So that is there's a couple methods for solving quadratics, but these only work when we have pretty specific forms, right? Our first, we just had only, right? The b term was 0. When the b term is 0, when b is equal to 0, it's a pretty standard thing. You've got just a squared term and a constant, so it's pretty easy to solve that. Here we had it nicely packaged in this in these parentheses that made our work easier. Sometimes it doesn't come that way though. So we're often going to have the problem exactly as I had written above, where we have, whoops, forgot my squared. We're trying to solve this kind of equation, okay, where A, B, and C are all not 0, okay, right? So we've got more things to deal with. And then things get a little trickier. And there are several ways to deal with this. And we're going to do one of them in this video. We'll do the other ones in the next video. The way we're going to deal with this is we're going to imagine what we wish we could do. And by that, what I mean is I want to figure out a way to rewrite this thing. Right? And we're going to kind of think about what we had up here. It's something similar to this up here, this 2x minus 3 squared, where our expanded polynomial was packaged into a smaller, simpler quantity. We want to try to package this one into a smaller, simpler quantity. We cannot expect that it's going to be as simple as that one where it's squared, but what we can hope for is that we can write it in the following form. Right? The product of two linear functions, two linear expressions, right? Ax plus b and cx plus d, right? So just note that the lowercase letters are different values. So a, b, the lowercase a, b, c, and d, they're not related to the capital A, B, and C, at least not directly. We're going to see how they are related in a second. So what our hope is that we take something that's given to us in the form on the right, on the left, and we are able to write it in an equivalent, write something equivalent in the form on the right, meaning they're the same thing, just written differently, right? This is we call this factoring. It's very similar to the idea that I can write 8 as 4 times 2, right? I can find two numbers that multiply together to get 8. I want to find two quantities like this that on the right that multiply together to get the quantity on the left. So how do I figure out what to choose for these values? Well, let's pretend for a second I've figured it out. Let's expand it. So ax times cx will give me acx squared. I'll get ax times d gives me a dx. I'll get b times cx to give me b cx, and I'll get b times d. Okay. So let's do a little work here. We've got acx squared plus ad plus bcx plus bd. Okay. So this constant here, let's write this on. This is all still equal to what we have on the left. This constant right here, lowercase a times lowercase c, has to be the same as capital A. This lowercase ad plus bc has to be the same as capital B. And lowercase b times d has to be the same as lowercase c, right? The coefficient of x squared on the left has to be the same as the coefficient of x squared on the right. The coefficient of x on the left has to be the same as the coefficient of x on the right. The constant term on the left has to be the same as the constant term on the right. And this is what gives us our map for telling us, remember, we have to choose lowercase a, b, c, and d. So how do we figure out how to choose them? Well, according to this map, the product of a and c has to equal capital A. In other words, we look at that coefficient of x squared, and we have to choose among the factors of it for lowercase a and c. When we choose b and d, we have to choose them so that they multiply into capital C. Okay. And then finally, we have to pick one from each. So we take A from this factor set and D from this factor set and get their product. And we take C and B from this factor set to get their product. And these have to sum to equal our coefficient of X, our capital B. Okay. Now, that probably sounded like a mess, right? There's just a whole bunch of words in there. Here's the truth of it. We never have to do this. We'll see in the next video. We have a foolproof method for solving these. We do this when what sounds to be a complicated process turns out to not be that complicated. It's possible very often to do this. I mean, really, it's always possible, or it's possible under certain conditions all the time. But usually, finding these factors can be pretty tricky. We're going to limit ourselves to when we have whole number factors and we find them easily to do these things. So, but when you can do it, when you can find them, it is a much faster method than some of the other ones to some degree. So let's do an example to make this clear. So suppose we were trying to solve the following. 6 is equal to 0. Okay, we wanted to solve this. So we're going to look to write the expression on the left, x squared plus 5x plus 6, as the product of two linear expressions. Okay, so what do we're trying to find out what are a, b, c, and d. Well, what we know is that a times c has to equal the coefficient of x squared, right? I didn't put it there, but there's a 1 there. So we know a times c is 1. Okay. We also know that b times d has to be 6. Okay. So what are our possibilities for a and c? The only possibilities we have are 1 and 1. 1 times 1 is 1. And -1 times -1 is 1. That's the entire list of all of our factors. Okay. And for a variety of reasons, -1 and -1 is just really never going to come up. If it did, we could get rid of it. So it really isn't something we have to worry about here. But let's pretend we do have to worry about it. Let's look at our factors of 6. We have 1 and 6. We have 2 and 3. Right? What we're going to do, remember what we do, is we pair one factor from that's part of we're going to take one, let's say it this way. We're going to take one factor from one of these pairs. So we're going to look at both of these pairs. Like if I'm looking at these pairs, I'm going to choose one of these. In this case, they're both the same, so it doesn't really matter which one I choose. And pair it with one of these. And then pair the other one with the other one and see if they add up when we multiply them together to that middle term. So if I was looking at the factors 1 and 6, I could look at the combination 1 times 1 plus 6 times 1 and see that we get 7. And there's no, we don't have to do anything else here because since the factors on the left, since the a times c they're both 1, there's no other combinations possible. It can't be that, right? And as probably most of you have already figured out, this is a pretty straightforward one. These factors will work because if we take 1 times 2 plus 1 times 3, we get 5. Sorry, that's a bad shade of green for showing up. 1 times 2 plus 1 times 3 is equal to 5. Okay? And so those are the choices we're going to make. That gives us our A, B, C, and D. So what we've determined is that x squared plus 5x plus 6 is equal to x. So I'm choosing A for x, sorry, A to be 1, and just not writing it. B will be 2. C will be 1 again, and D will be 3, right? So I've just plugged in 1, 2, 1, 3, okay? And of course, we can always check our work. X times x gives me x squared. X times 3 gives me 3x. 2 times x gives me 2x. 2 times 3 gives me 6. And we get x squared plus 6. 2 plus 3 is not 6. 2 plus 3 is 5. Plus 6. Okay, which is indeed equal to what we started with. Okay. So now that we've factored, let's remind ourselves what we were trying to do in the beginning. So we've got x squared plus 5x plus 6 is equal to this expression. I meant this line. Of course, it's equal to itself, but it's equal to this factored form. Remember what we were trying to do. We were trying to solve this equation. X squared plus 5x plus 6 is equal to 0. Well, now that I know that this factored form is equivalent, I have x plus 2 times x plus 3 is equal to 0. And now we're going to use a nice little fact that only works with the number 0, right? This is why we look for this form where we have 0 on the right. If I have two things multiplying together to be 0, then it must be the case that one of them is 0. It has to be true that B is 0, A is 0, or B is 0, right? It could be the case that both of them are. We always have an inclusive or, unless I say otherwise, but if I just use or casually, I mean inclusive. So it could be the case that both of them are 0, but at least one of them is 0, okay? So in the case of this expression, this equation, that means that we have to have x plus 2 equal to 0, or x plus 3 equal to 0. And these are both straightforward equations to solve. So we have two solutions. X is equal to -2, or x is equal to -3. Let's do the extra step of checking our work. So when x equals -2, we get -2 squared plus 5 times -2 plus 6. This gives us 4 minus 10 plus 6, which turns out to be 0, right? And that's what we expected to see. Let's do the other one. X equals -3. We've got -3 squared plus 5 times -3 plus 6. That gives me 9 minus 15 plus 6, which you can see is also 0. And so these are our two solutions. Okay. All right. So far, so good. Let's ugly things up just a little bit. Let's take a look at x squared minus 5x plus 6 equals 0. So all I've done is change that middle term from a positive to a negative. Actually, I'm gonna change this a little bit. I'm gonna do something on the fly. Let's do x squared minus x minus 6. All right, that's what I want to write. Okay, so we got to play the same game. We're going to try to write, let's do this work over here, x squared minus x minus 6 as ax plus b times cx plus d. Okay, now we know that a times c has to equal 1, and we said last time it's got to be equal to 1 and 1, or negative 1 and negative 1. Those are the only possibilities. Now, we could actually make both of these work here, I believe, but it's going to turn out whenever we have an x squared here, we can always choose this one. I hinted at this last time. I think it's just a safer bet to say we can always choose this. If a and c are 1, we can just if their product has to be 1, if the coefficient is a 1, we could just have a and c be 1. So we can simplify these cases to just saying we're looking for this. So with that in mind, then we know we need b times d to equal negative 6. And we need AD plus BC to equal negative 1, this middle term. Right? That's the little map that we had. But of course, in this case, A and C are both 1, so this simplifies to just saying D plus B has to equal negative 1. So what are our choices for B and D? Well, since they multiply to be negative 6, they're either negative 1 and 6, 1 and negative 6, 2 and negative 3, negative 2 and 3. And so all we're looking for is a pair of these so that their sum is negative 1. And it's pretty simple to see that that has to be the case, that D plus B has to be negative 1. We have to have 2 and negative 3. So we're just going to have a 2 and a negative 3 for B and D. So what this is going to look like is x plus 2 and x minus 3. Let's just double check by multiplying this out. We've got x times x is x squared, x times negative 3 is minus 3x, x times 2 is plus 2x, 2 times 3 is negative 6, and this indeed is x squared minus x minus 6. Which means we can now substitute this expression in for the one we started with. So this becomes x plus 2 times x minus 3. And we use the same idea that if this product of these two things is 0, then one of them must be 0. And this gives us solutions x equals negative 2 or x equals 3. Okay, I'm going to leave this one for you guys to check so we can get to our last case. This will be my last example where we really complicate things. Let's grab a copy of our rules just so we can have it nearby when we're doing this one. Quick copy. All right. And there we go. Okay, just going to leave this, shrink it down just a little bit. All right, just leave that up there to reference when we need to. So here is our last example. We have 4x squared plus 13x minus 12 equals 0. And our strategy is we're going to want to write 4x squared plus 13x minus 12 as something like ax plus b times cx plus d. Okay, so let's see what we need to do here. So I know using my map over here, I see that I need the product of a and c. I need a and c to be equal to the coefficient of x squared. So a times c has to equal 4. And I need the product of b and d to be equal to the constant term. So in our case, that's negative 12. Okay. So let's write down our possibilities for a and c. A and c could be 1 and 4, and they could be 2 and 2. We could have both be negative in each case, but again, that's possible, but needlessly complicated. So we're going to just assume that they're all positive. B and D equals -12, though we do have to keep the negative in mind. So we're going to have the possibility that we have 1 and -12, or -1 and 12, 2 and -6, or -2 and 6. We're going to have 3 and -4, or -3 and 4, right? So what are we looking at these pairs for? Because we're going to take one. So on the left here, I've got all the factors of AC, all the factor pairs, and then I've got the factor pairs of -12 in this column. I'm going to take one from, I'm going to choose a factor pairing for, say, AC, and I'm going to try matching them with factor pairings over here and see if I can find combinations so that when I multiply one factor from each and then the other pair factors from each together and sum those, I end up with, in our case, 13, right? So it's a lot of words to say that we're going to pick one factor from each and multiply by the other factor of each, and then do that again and sum those to see that we get the term in the middle, the B term, or in our case, it's 13. So we're trying to sum up to 13. So let me do it, because it's obviously really hard to say that sentence for me, to show you what I mean. So if I look at, let's look at the factors 2 and 2. I could take 2 and 2, and I'm gonna pair them with this first thing. So I could take 2 times 1 plus 2 times -12 and see if I get 13, right? And we're going to do this quickly, but it's very clear that we're not getting that, right? This is 2 minus 24 is not 13. We can also pair. So again, to be clear, I'm taking 2 and 2 here and doing 2 and 2 there. Let's try it again with -1 and 12. So I did it with the first terms, or the first pair of factors. I'm going to try it with this one, where I'll take 2 times -1 plus 2 times 12. And again, I'm not getting anything useful. This is 24 minus 2. It's not 13. Let's just do one more. 2 times 2 plus 2 times -6. We get 4 minus 12 is going to be -8. So again, that's not going to work. Now, in the interest of time, I'm going to not go through all of these, but we would want to check all of them. And as you do this more, you'll start to get faster at this and do a lot of it in your head. But you do want to go through and see if there's any possibilities. And it turns out none of them will work. And so we can eliminate 2 and 2 as possible values of A and C. So let's move on to 1 and 4, and now play this matching game with 1 and 4. So I'm going to move this out of the way, but let's do the same game. So if I've got 1 and 4, I'm going to take 1 and 4 and match it with these pairs of values. So we'll have 1 times 1 plus 4 times -12. And this is not equal to 13, right? Since my pair is now not the same, right? In the beginning I had 2 and 2. I also have to try the other matching. Since 1 and 4 aren't the same, I have to try matching 1 with -12. Sorry, that should be a negative. Screwy. 1 and -12 plus 4 times 1. Right? So again, let's just be clear. These are the factors. 1 and 4 are the factors of 4. 1 and -12 are the factors of -12. Here I have 1 and 4, -12 and 1. But in both of these cases, we don't get 13. Right? So we would go through checking all of these. Again, I'm not going to do each and every one. Let's do one of these. Let's look at this pair. Let's try checking that one. So we would do 1 times 2 plus 4 times -6 does not equal 13. We would also do 1 times -6 plus 4 times 2. This also does not equal 13. So we keep checking like this. We keep checking like this, going through all of our different options. Let's jump to the end here. Again, I'm going to move these out of the way. we've got, so I'm going to look at these last two options now, starting with its first one. We've got 1 times 3 plus 4 times -4, right? And if you notice, 1 times 3 plus 4 times -4, we get 3 minus 16 is -13. That feels pretty hopeful. If we take the other sign, if we look at, if we put the negative on the 3, let's see what happens. 1 times -3 plus 4 times 4, this is equal to -3 plus 16, which is equal to 13. Okay, so now we've found something that works. So let's label everything to make sure we have this right. So I had A and C here, A and C here, and then this will be my D and B, right? I'm just following this little map. I found a combination of these factors to get to add up to 13. So it's a lot, but well, let's just put it in, and then we'll see what we can do next. So now that we have our values, I'm going to write this. Things are getting messy. Let's erase a few things. So let's erase all this scratch work. Okay, let's take this equation over here. So now I've got my values of A, D, C, and B. Let's just write them in. So A is 1, so I'm not going to write that. B is 4. C is 4, so I get 4x, and D is -3, and I get -3. And so now our claim is that according to the rule we've set up, 4x squared plus 13x minus 12 should be equal to x plus 4 times 4x minus 3. The simplest way to see if we've done it right is to check our work, right? X times 4x squared, or x times 4x gives me 4x squared. X times -3 gives me -3x. 4x times 4 gives me 16x. And 4 times -3 gives me -12. And so I get 4x squared plus 13x minus 12, which is exactly what we were hoping for. So we did it, right? It is a slog. We've still got to finish this, but I'm just going to say it's a slog to go through all of these things. There are different methods out there. I've seen a million of them, and you're welcome to use any that you find that work for you. I essentially do this. I do it a little bit in my head, or I usually end up just writing a couple of the factors in front and putting the other two in and seeing what happens and playing with the combinations. There's just no substitute for practice. So the more of these you do, the less daunting it will seem. But in the beginning, there's just a lot of meticulously checking through all the combinations you can come up with. Okay, now that we have this factoring, let's finish this problem up. We've got x plus 4 times 4x minus 3 is equal to 0, which means that x plus 4 must be equal to 0, or 4x minus 3 must be equal to 0. This gives me x equals -4, or we have 4x equals 3, which gives me x equals 3/4. So our answers are x is equal to -4 or 3/4. And those are the two possibilities. I'm going to end it here. We should throw that back in. Let's do one of them. Let's check one of them, and I'll let you check the other. I'll check the easy one, the -4. Maybe that's the easy one. So we've got, so we're going to check x equals -4. We'll have 4 times -4 squared plus 13 times -4 minus 12. Well, what's 4 times -4 squared? That's 4 times 16. 13 times 4, so that's -52 minus 12. 4 times 16 is 64. Minus 52 minus 12 is -64, and that indeed is equal to 0. So I'll let you check 3/4 and see that that one also turns out to be 0. Okay, that is it for this one. Thanks, everybody. I will see you next time.